Picture a rocket climbing at 3,000 miles per hour. Inside its engine, a material is vanishing. Not failing. Not cracking. Vanishing, by design, at roughly 1 inch every single second. The engineers who built that engine knew this would happen. They planned for it. They needed it to happen. Because without that controlled destruction, the whole machine would tear itself apart in a different way entirely. Every machine on this list was built to consume part of itself in order to function. Not a flaw. Not a compromise. The self-destruction is the design. These are 9 machines where the engineers looked at the physics, looked at the forces involved, and decided the only solution was to build something that eats itself alive every time it runs. Starting with number 9. A shaped charge drops into a borehole nearly 2 miles underground. It sits in total darkness, surrounded by rock and steel casing, at temperatures that would warp an ordinary tool. Then a signal arrives. And in roughly 1/10,000th of a second, it is gone. Oil wells are not simply drilled and opened. The steel casing that lines the borehole has to be punctured at precise depths to let petroleum flow into the well. The tool that does this is called a perforating gun, and it is a single-use explosive device lowered on a wireline into the completed well. Each perforating gun carries a row of shaped charges, small, precisely engineered explosive lenses that focus their energy into a jet of metal traveling at roughly 25,000 feet per second. That jet punches a clean hole through the steel casing and several inches into the surrounding rock. The charges fire, the holes appear, and the gun body is left as a shredded wreck at the bottom of the hole. There is no second use. No reloading. The destruction is the job. The false belief here is that oil wells are opened gently, like a tap. In reality, they are stabbed open by a tool that annihilates itself to do it. Number 8. An avalanche cannon sits alone on a ridge above a ski resort in the Swiss Alps. Winter. 3 in the morning. A technician sends a signal, and a single artillery shell detonates against a loaded snowfield. The controlled avalanche runs harmlessly into a catchment zone before the lifts open. The cannon barrel is examined afterward. The rifling inside has worn a little more. The heat from thousands of firings has taken its toll. But the barrel itself was expected to have a finite service life measured in total rounds, not years. Avalanche-controlled cannons used at resorts and mountain passes are purpose-built artillery pieces. They fire live explosive shells, and like any gun barrel, the bore erodes with every shot. Propellant gases at temperatures exceeding 5,000 degrees Fahrenheit scour the rifling with each firing. Most avalanche cannon operators track total rounds fired and replace the barrel on a fixed schedule, not because it fails suddenly, but because accuracy degrades predictably as the steel is slowly consumed from the inside. The barrel is not failing. It is being used up, and the engineers designed a replacement interval around that known rate of consumption. Number 7. A spacecraft sits on the pad at Kennedy Space Center. When it launches, it carries several Pyrotechnic stage separators, small explosive devices arranged in rings around the joints between the rocket stages. When the first stage exhausts its fuel, these devices fire simultaneously. The joint severs cleanly. The spent stage falls away. And the explosive devices that created that separation no longer exist in any useful sense. They are consumed in the act. Stage separation is one of the most critical moments in any launch, and it is entrusted entirely to single-use explosive components because nothing faster or more reliable exists. On the Saturn V rocket, the separation between the first and second stages used a linear-shaped charge called the mild detonating fuse system, combined with Pyrotechnic retrorockets. The timing window for clean separation is measured in milliseconds. A mechanical clamp or bolt would take too long and could jam. The explosive devices cannot jam. They fire, they consume themselves, and the stages part. Every launch vehicle from the Falcon 9 to the Ariane 5 uses variations of this same principle. The self-destruction is the only mechanism reliable enough for the job. Which of these machines would you least want to be standing next to when it fires? Tell me in the comments. Number 6. An explosive bolt on a launch vehicle looks, from the outside, like an ordinary fastener. It holds two massive structures together with tens of thousands of pounds of clamping force. Then a signal arrives, a small charge inside the bolt fires, the bolt shears through itself, and the joint releases in under 1 millisecond. Explosive bolts and separation nuts are used wherever a connection must hold with absolute rigidity and then release with absolute certainty. NASA used them to hold the Saturn V rocket to the launch platform, roughly 3 dozen hold-down bolts, each loaded with a Pyrotechnic cartridge. At the moment of launch commit, all bolts fired simultaneously. The rocket was held to the pad until thrust was confirmed, then released in a single instant. The bolts were destroyed. They were designed to be destroyed. Engineers refer to this as a one-shot device, and the engineering philosophy behind it is deliberately blunt. A component that can only ever fire once will never fail to fire due to wear, contamination, or fatigue. The self-destruction guarantees the reliability. Number 5. A naval railgun prototype sits in a test facility at Dahlgren, Virginia. It fires a projectile at roughly 5,000 miles per hour using electromagnetic force rather than chemical propellant. The projectile travels downrange successfully. The barrel is then inspected. Inside, the conducting rails that accelerated the round are scored. The surface has ablated. The railgun barrel used in the United States Navy experimental program required replacement after roughly 400 to 600 shots, not because it failed unexpectedly, but because the arc of plasma created between the rails and the projectile erodes the rail surface with every firing. The engineers knew this going in. They designed for a finite barrel life, not an infinite one. Number 4. A solid rocket booster ignites. Inside, roughly 1,000 tons of propellant begin burning at temperatures near 5,500 degrees Fahrenheit. The exhaust has to travel through a nozzle. That nozzle is lined with an ablative material, a carbon composite that chars and erodes in a controlled way. The erosion rate is roughly 1 inch per second at peak burn. The nozzle liner is deliberately sacrificed to protect the structural nozzle behind it, while also maintaining the precise throat geometry the engine needs to produce thrust. The Space Shuttle's solid rocket boosters use graphite epoxy ablative liners in their nozzle throats. Engineers measured post-flight erosion to the thousandth of an inch and used that data to calibrate the next flight's liner thickness. The liner was supposed to erode. It was manufactured to erode at a known rate and no faster. Everyone assumes the toughest material wins in engineering. Here, the opposite is true. A softer, sacrificial material saves the harder structure by absorbing the heat load into its own destruction. Number 3. A reentry heat shield. The Apollo command module enters the atmosphere at roughly 25,000 miles per hour. The air ahead of it cannot move out of the way fast enough, and it compresses into a plasma sheath reaching temperatures of roughly 5,000 degrees Fahrenheit. The shield on the blunt face of the capsule is made of an ablative material called avcoat, a silica fiber and epoxy resin compound that chars, then gases off. The gaseous layer carries the heat away from the capsule surface. The shield does not reflect heat. It does not insulate heat. It converts itself into gas and carries the heat with it as it leaves. The Apollo 11 command module's heat shield ablated away roughly 1.5 inches of material during reentry. That consumption was the protection. The more it burned away, the more it was working. Number 2. An oil well blowout. A wireline truck sits at the surface. Deep below, a bridge plug is being set to isolate a section of well. The plug is seated using a setting tool that fires a propellant charge to drive the plug slips into the casing wall. Once set, the setting tool is retrieved, but the propellant case inside it is spent, split, and deformed. Single use. The well plugging industry relies entirely on consumable pyrotechnic tools because the pressures involved, sometimes exceeding 15,000 pounds per square inch, demand a setting force that no hydraulic tool can deliver reliably at that depth. And number 1. The solid rocket motor itself, not just the nozzle liner, but the motor case insulation. The propellant grain is bonded directly to a rubber-lined steel or composite case. As the propellant burns from the inside out, the insulation layer between the flame and the case wall is consumed millimeter by millimeter. On the Space Shuttle solid rocket boosters, this insulation was roughly half an inch thick in some sections. It was designed to survive just long enough, just barely long enough, for the burn to complete before the casing wall reached its structural limit. The engineers calculated burn time, erosion rate, and case temperature simultaneously, then manufactured the insulation to disappear at exactly the right moment. Not a moment too soon. Not a moment too late. The most powerful motors humans have ever built were kept alive by a material designed to cease to exist precisely on schedule. That is the hidden engineering in all 9 of these machines. The self-destruction is not a side effect. It is the mechanism. The material that ablates, erodes, chars, or detonates is not failing. It is succeeding at the only job it was built to do, absorbing an energy load so extreme that no permanent material could survive it. The engineers did not overcome these forces. They negotiated with them, and the currency they used was controlled, deliberate, calculated destruction. The bigger the machine, the simpler the trick that makes it work.